Assalamu alaikum. My name is Mohammed Daniyal Niazi. My roll number is 23 ME56 and I am leader of this uh, presentation. Uh, Today uh, we are presenting a project on engineering economics, but instead of just reading the formulas of a slide, we're going to show you how each chapter concept applies to real business decision. Every chapter you are about to see is paired with different industry, uh, technology, agriculture, oil and gas, government infrastructure, and more. So you can see that engineering economics isn't just math. It's how real companies decide where to build their money. So let's start with chapter number one. In chapter number one, uh, uh, it is basically about foundations of engineering economy. I have case study of ride-hailing startup fleet decision. Imagine a ride-hailing startup similar to Cream that wants to launch its own vehicle fleet instead of relying only on partner-owned cars. Before making the decision, the finance team has to follow the exact steps we see in chapter number one. Uh, they will have to uh, identify the problem, gather cash flow data, list alternative, and estimate interest rate they will pay on financing. For example, a company borrows money to buy cars, so the interest rate tells them the cost of borrowed capital. If they instead invested the same money in saving instrument, the rate of return would tell them what they would earn. This is the core idea of chapter number one. Every rupee has a time value, and cash inflows and outflows must be mapped on a cash flow diagram before any comparison can be made. The startup's initial vehicle purchase is an outflow, and monthly ride revenue is um, an inflow. That's the foundation everything else in this course builds on. So now we move toward chapter number two. Chapter number two is about equivalence factors and symbols. In this chapter, I have case study of textile export companies equipment loan. Now let's move to Pakistan textile export sector. A garment factory in Faisalabad wants to take loan to buy new stitching machines. The bank gives them a fixed loan amount today, that is P, and expects a series of equal payments, capital A, over the next 5 years. This is exactly where chapter number two's A by P factor uh, involves. Uh, a, Converting a present loan amount into an equivalent uniform annual payments. If the factory instead wants to know what a machine bought today would be worth in future value terms after 5 years of use, they would apply F by P factor. uh, F by P factor is here, so they will apply this. And if they are relying with a project where cost increases every year, say maintenance cost rising steadily, that's where arithmetic gradient would be applied uh, there. So arithmetic gradient would be applied, that is capital G, comes in while the cost rising by a fixed percentage each year like rent uses, and the geometric gradient, that is small g, and these factors let engineers translate money across different projects in time using one consistent mathematical language. Now we move towards um, chapter number three. In chapter number 3, we would study combining and shifting um equivalence factors. I have case study of solar power project with delayed subsidy. Consider a solar energy company installing rooftop panels for a housing society. The government offers a subsidy, but it only starts from year 4 and continues to year 10. That is shifted uniform series. This is precisely chapter three's challenge. Real cash flows are rarely simple single payment. Here we have initial installation cost, single capital P, a shifted subsidy, uniform series starting late, and a salvage value when panels are eventually replaced. Using the superposition principle, we can the company can calculate the present worth of each piece separately. The shifted capital A is first moved to year 3 using P by a factor, and then uh, it is uh, and adds that P by F factor adds them together. This mirror real solar and infrastructure financing where public support always doesn't uh, start from day one. So we move toward chapter number 4, that is about nominal and effective interest rates. In this, I have case study of bank comparing credit cards and loan offers. There would be two same cards, but the contract policy would differ. Let me explain this. Like, let's shift to consumer banking. A bank advertises a credit card with 12% annual interest, but is it compounded monthly, quarterly, or daily? This is where chapter 4 becomes essential. A 12% nominal rate compounded monthly doesn't cost the same as 12% compounded daily. The effective annual rate um, will eventually actually be higher the more frequent interest compounds, climbing to 12% annually to 12.75% under daily compounding and reaching its mathematical ceiling under continuous compounding for a consumer comparing for a customer comparing two credit cards with the same advertised rate but different compounding period, converting both effective annual rates is the only fair way to compare. And it's exactly the trap many people fall into when reading the fine print on loan contracts. Uh, See, like annually it's 12%, then for daily it's 12.75%. That is a trick that a bank uses. Now we move towards chapter number 5. Uh, In chapter number 5, I have we will discuss present worth analysis. I have case study of government highway and dam project. Now for public infrastructure, uh, uh, government plans a dam or highway meant to serve the public uh, indefinitely. Engineers can't just calculate present worth for fixed number of years. They need capitalized cost, the present worth of project assumed to last forever. This is chapter 5 specialty, comparing project alternatives using present worth analysis discounted at the minimum attractive rate of return, and that is denoted by capital MARR. For cost only public projects where government isn't earning revenue, just providing a service. The rule is to pick alternative with the lowest cost, but when two dam design designs have different lifespans, and the government must evaluate them over their least common multiple, ensuring a fair for like like comparison rather than comparing a 20-year design to a 40 years one directly. This is the idea of chapter number uh, 5. After that, we move towards chapter number 6. In chapter number 6, we have annual worth analysis. In I have case study of a logistic company's truck fleet decision. Picture a logistic company like TCS or Leopard's Courier deciding between two truck models. One has a 4-year lifespan and the other has 7-year lifespan. Comparing these with present worth would require finding their least common multiple, which is messy. Uh, this is where chapter 6 annual worth uh, analy- analysis shines, since annual worth converts everything into yearly cost. When life cycle tells the whole story. No LCM needed. The company calculates capital recovery, that is denoted by CR, and which represent the annualized cost of owning each truck, accounting for its purchase price, salvage value, and required return. Which truck has the lower total annual worth? Capital recovery plus operating costs is a more economical choice. This is also the exact method fleet managers actually use to decide when to standardize on one vehicle brand. Now we move toward chapter number 7. In chapter number 7, we have internal rate of return analysis. I have case study of oil and gas drilling project, one of the major uh, domain I want to pursue. Let's look at the energy sector. An oil drilling project often has strange cash flow pattern, a large upfront cost, several years of revenue, then a large cost again for well capping and environmental restoration. This creates a non-conventional cash flow with more than one sign chain. Chapter number 7 tells uh, um, us that it tells us under discrete rule of signs. This pattern can produce multiple rate of return, uh, meaning the standard IRR equation might solve two different valid interest rates, neither of which is economically meaningful on its own. Engineers resolve this issue using the external rate of return. Uh, uh, method ERR method is basically discounting all outflows at the financing rate and compounding all inflows at the reinvestment rate, then solving for a single rate that equates the two. This is real limitation oil and gas financial analysts deal with uh, constantly. Like this is problem they face every day while analysis. Now we move towards chapter number 8, that is basically about rate of return for multiple alternatives. I have case study of a tech company choosing data center investments. Uh, Imagine a tech company deciding between a smaller data center upgrade costing $1 million with a 50% individual rate of return versus a much larger uh, $100 million data center expansion with only a 20% individual rate of return. Chapter number 8 explains uh, why you cannot just pick the option with the higher percentage return. That's the fallacy of direct comparison. If, because it ignores the scale of investment. Instead, the company calculates the incremental rate of return on the extra $9 million required for the bigger option. If the incremental cost still exceeds the company's MARR, the larger, higher cost projects actually the better decision. Even though its standalone ROI looks smaller, this is exactly how corporations justify large capital expansion over smaller, flashier ones. In chapter number 9, we have benefit cost analysis. I have case study of metro bus transit project. Public transit project. Now consider a government funded metro bus project. Unlike a private company, the government doesn't measure success in pure profit. It measures public benefit against public cost. Chapter number 9 benefits. Uh, uh, Chapter 9's benefit cost ratio captures this perfectly. Benefits include time saved by computers, uh, uh, customers, and reduced traffic accident. This benefit might include noise and property acquisition, and costs are the construction and maintenance expenses, all converted to present worth. If the B/C ratio is greater than or equal to 1, the project is considered economically justified for the public. When comparing two um, transit routes, the government uses incremental B/C analysis, um, and just like the incremental ROR method to avoid the same isn't always better on bigger isn't always better on paper trap. Now we move toward chapter number 10. In this, it discusses WACC and capital financing. WACC is basically weight average cost of capital. Consider uh, my case study in automotive manufacturer building a new plant. In this, consider manufacturer building a new assembly plant financed partly through bank loans, debit, and partly through issuing shares equity. Chapter 10's weight average cost of capital formula blends the cost of both funding source, weighted by how much of each is used, and accounts for the fact that debit interest is tax deductible. This weight average cost capital becomes the company's true cost of raising money, and their MARR for eventually the new plant projects must always be set above this WACC, or company would be destroying value by investing in the rate of uh, investing at a return lower than what it cost them to raise the capital in the first place. This single number drives virtually every major investment decision automotive companies make. Now we move toward chapter number 11. In chapter number 11, it discusses about replacement decision and economic service life. Case study, a farmer deciding whether to replace old tractors. In agriculture, a farmer owns an aching tractor, the Defender, the becoming expense to that's becoming expensive to maintain, while a newer, more fuel-efficient tractor, the Challenger, is available to the market. Chapter 11 becomes clear that whether the farmer originally paid for the old tractor is a sunk cost and must be ignored. Only its current trade in value matters. The farmer calculates economic service life and the ownership duration minimizes uh, uh, total annual cost, balancing um, declining capital recovery cost against rising maintenance expense as a tractor ages. This U-shaped cost curve tells the farmer exactly when replacing equipment, not sooner, not later. Makes the most financial sense. Now we move toward chapter number 12, and that is capital budgeting and rationing. I have case study of e-commerce company with a limited budget. Picture an e-commerce platform like Draz with 10 independent potential projects, a new warehouse, app features, delivery fleet expansion, but only a limited annual budget to fund them. Chapter 12 is capital uh, rationing problem applies directly here since these projects are independent, not mutually exclusive. The companies can't just fund every project with a positive present worth using a linear programming model, and they select binary combinations of projects that maximize total present worth while staying within the budget constraint. This is real mathematics behind how large companies build their annual investment portfolios when demand for capital exceeds supply. In chapter number 13, it discusses about break-even and payback analysis. I have case study of a new restaurant branch opening. Financially, uh, if imagine an entrepreneur opening a new restaurant branch before signing the lease, they need to know two things: how many meals must be sold per month just to cover cost, and how long it will take to earn back the initial investment. Chapter 13 answers both. The break-even quantity is founded by dividing fixed cost by the difference between the price and a variable cost per meal, telling the owner the minimum sale volume needed. Separately, payback period analysis estimates how many months of net cash flow it takes to recover initial investment, when the discounted payback version being more realistic since it also accounts for the time value of money. Almost every small business owner performs some version of this analysis before committing capital. So, in this 13 case studies, we have seen engineering economics applied to a ride-hailing startup, textile factory, solar energy, banking, government infrastructure, logistics, oil and gas, big tech, public transit, automotive manufacturing, agriculture, e-commerce, and small restaurant. The math stays the same: present worth, annual worth, rate of return. But the decision it drives through and it drives and touch nearly every industry in the real economy. So that these were my case studies. Thank you for the watching. Now I will add the video of Syed Kazim and Shah. Its roll number is 23 and me 45, and he would give his own case studies. Thank you very much.
Bismillah Rahman Rahim. Assalamu alaikum everyone. My name is Syed Kazim Shah. Today I am going to present my topic on engineering economy. So this presentation is based on chapter number 1 to 13 of engineering economy. In this presentation I will explain the basic concept and show how engineers use them to make the smart financial decision. So let's begin. Uh, so now we will discuss. First thing is engineering economy. So engineering economy is a study of making the best financial decision in engineering project. It helps engineer to compare different alternative and choose the best option based on the cost, benefit, and future value. Instead of making decision by guessing, engineers use economic analysis to select the best project. Now let's look at the course overview. So this is our course overview. This presentation cover chapter number 1 to 13, and these chapters include engineering economic fundamentals, interest, cash flow, present worth analysis, rate of return, benefits, replacement analysis. So all these topics help engineer to make the better financial decision. Now let's move to first important topic, that is engineering economy. So engineering economy is a study of choosing the best solution for from different engineering alternative. It helps engineer to reduce cost and increase profit. This process include identifying the problem, finding different alternative, comparing cost and benefits, and selecting the best option. Let's take an example to understand this engineering economy. Suppose a company wants to buy one of the two machines. Engineering economic help the company to choose the machine that give better performance at a lower total cost. So now move to next slide, that is interest rate and rate of return. So now let's discuss interest rate. The interest rate is the cost of borrowing money or be rewarded by for investing money. The rate of return shows how much profit we can earn from an investment. Let's take an example. If we invest 100,000 today and receive 110,000 after 1 year, so we earn a return of our investment. These concepts help engineer to evaluate investment project. Now move to next slide, that is economic equivalence and cash flow. So now let's move to economic equivalence. Economic equivalence means comparing money received at different times. This is based on time value of money, which says the value of money today is worth more than the same amount in the future. So cash flow diagram shows when money enters or leave the project. So this all help engineer to understand project cost and benefit clearly. Now move toward our next slide, that is simple interest and compound interest. So basically these are two types of the interest. The first is simple interest, which is calculated only on its original amount, and the second one is compound interest, which is calculated on both the original amount and the previous interest. So compound interest grows faster, and is economically used in banks and engineering project. So now move to our slide number 8, that is single payment factor. So this slide explain all about the single payment factor. So the f given p factor convert present value into future value, and the p given f factor convert future value into the present value. These vectors are useful when only one payment is involved. They help engineer or economics compare money at different points in a time. In a timeline, with the help of these two formulas, we compare the money. So now we move to our next topic, that is uniform series factor. So sometime we pay or receive the same amount every year. This is called uniform series. The P given F factor convert equal yearly amount into a present worth, and the A given P factor convert present value into equal annual payment. These factors are commonly used in engineering project. So now move to our next slide, that is modeling gradient cash flows. So sometime project cost increase every year instead of staying the same. This increase is called gradient, and there are two common types: arithmetic gradient and the geometric gradient. These model help engineer analysis project where cost or income change over time. So this is our modeling, and now we go to our next slide, that is determining interest rate or number of periods. So sometime we already know the present value, future value, and cash value, but we do not know the interest rate or the number of years. So in this situation, we calculate the unknown value by using engineering economic formulas or financial tables. This help engineer to estimate project duration or expected return. Let's take a daily life example to understand it. Suppose I invest rs 100,000 today. After some years it become 150,000. So now I want to know what interest rate I earned or how many year it took. So engineering economic help to calculate it easily, formulas and tables. So now move to our next slide, that is combining multiple equivalence factor. So, in a real engineering project, we usually have more than one cash flows. Some payments are made today and some are received every year. So, some are received at the end of the project. Instead of solving every cash flow separately, we combine all equivalence factor. This make calculation easier and reduce mistakes. Let's take an example. Suppose a company buy a machine. It pays the purchase price today. Every year it pays maintenance cost. At the end of the machine life, it also receive a salvage value. To find the total economic value, we combine all these cash flows into a one analysis. So now move toward our next slide, that is handling shifted uniform and grading series. Sometimes equal yearly payments do not start immediately. They may start after 1 or 2 years. So this is called shifted uniform series. Sometimes payment increase every year. This is called gradient series. So these situations are common in engineering project. So example, if we take that is, suppose a company give yearly maintenance after the second year. So or suppose maintenance cost increases by 5,000 every year because the machines become older. So engineering economic provide formulas to analyze both situation correctly. So now move to our next slide, that is nominal and effective interest rate. So these are the two type of interest rate. The first is the nominal interest rate, and the second one is effective interest rate. Nominal interest rate is a stated annual interest rate. Effective interest rate is actual interest rate earned after considering compounding. So the effective rate is usually higher because interest is added more frequently. If we take example that if a bank advertises 12% annual interest compounded monthly, and the actual return is slightly more than 12%, the actual return is called the effective interest rate. Now the next slide is effective interest rate formulation. So the effective interest rate help us to compare different investment option fairly. Different banks may use monthly, quarterly, or yearly compounding. So instead of comparing nominal rate, engineer compare effective rate. If I take example that if we have two bank A offer 12% compound yearly, and bank B also offer 12% but compounded monthly. So, although both advertise 12%, but bank B gives slightly higher return because they compounded monthly. Then our next slide is continuous compounding. Continuous compounding is an advanced concept. It assumes that the interest is added continuously instead of monthly or yearly. This gives the maximum possible growth of money. Although it is not a common in daily banking, it is used in finance and engineering analysis. Now, our next slide is we're going to discuss is present worth analysis. Most important, present worth analysis is one of the most important tool in engineering economics. It convert all the future cost and future benefit in today values. Then engineer compare different alternative. Usually the project with a better present worth is selected. Then we have evaluating alternative with different lives. Sometimes two machine perform the same work but have different lifetime. One machine may last at let's suppose 5 year, and another may last at 8 year. In this situation, we cannot compare them directly. Engineering economic provide methods such as least common multiple approach or reinvestment assumption to make a fair comparison. Then we have next slide, that is capitalized cost. Again, is a very important tool in engineering economics. If we take an example that like uh, like highways, dams, bridges, and public water supply system projects, they these projects require maintenance for many years. So capitalized cost help estimate the cost, the total present value required to support such projects permanently. If we take an example, a city build a public bridge, the bridge may require to repair every few years for many decades. So using capitalized cost, engineer estimate the total money needed over its entire life. Then the next slide is annual worth analysis. Again, it's an important tool in engineering economics. So annual worth convert all the project cost and benefit into equal yearly amount. This make it comparison between different project very simple. The project with the better annual worth is usually selected. Then we have transition. So this is our next slide, that is transition and capital recovery formulation. Now let's discuss the capital recovery analysis. Capital recovery tells us how much money we must recover every year to cover the cost of an investment. It includes initial cost, interest rate, and the useful life of the asset. This method help engineer know whether an investment is financially sustainable or not. Then we have interest rate of return. In simple, we call it as IRR. The next important tool, most important, is IRR. IRR is the interest rate at which the present worth of an project becomes zero. In simple word, it tell how profitable project is. If the IRR is higher than the company requirement rate of return, then the project is usually acceptable. So now we have multiple rate of return. So sometimes project has both positive and negative cash flows at different time. In this situation, more than one IRR may appear. So this is called the multiple rate of return problems. So therefore, engineer do not really rely on only on the IRR. They also use present worth in annual worth analysis before making the final decision. So this give more reliable and accurate result. So then we have rate of return for multiple alternative. So in this, in a real engineering project, we usually have more than one options. For example, two different machines or two different investment plans. Instead of choosing randomly, engineer compare the alternative using the rate of return. The alternative with the better economic performance is selected. Then we have the incremental cash flow analysis. So sometime one machine is more expensive than another. The question is the extra cost worth paying? Incremental cash flow analysis answer is this question. Instead of comparing the total cost, we compare only the difference between two alternative. Then we have benefit cost ratio analysis. So benefit cost ratio is the another important decision making tool. It compares the total benefit with the total cost of project. If the benefit cost ratio is greater than 1, the project is economically acceptable, and if the it is less than 1, then the project should normally rejected. Then we have then we have next slide, that is incremental benefit cost ratio. So when comparing two projects, engineer often use to incremental benefit cost ratio. This method compare only the additional benefit and additional cost between the two alternative. It help us to choose the better project more accurately. This is the especially useful when both projects are economically acceptable. Then we have weighted average cost of capital, WACC. Now companies usually finance project using both debt and equity. So weighted average cost of capital represent the average cost of all these financial sources. It is commonly used in as a minimal acceptable rate of return. Then we have slide number 29, that is replacement decision. So machine do not last forever. As they become older, maintenance cost increases, inefficiency decreases, obviously. So engineer must decide whether they continues using the older machine or replace it with a new machine. So replacement analysis help us make this decision based on economic calculation rather than the personal opinion. Then we have capital capital budgeting. So every company has limited money but many possible project. So capital projecting help management decide the project should receive investment, and the project with the higher economic value and best financial performance are selected first. So this ensured that the company limited resources are used wisely. Then we have the next slide, that is break even and payback analysis. Finally, this is our payback or break even analysis, in which in this slide we discuss a break even analysis is that it tells us how many units must be sold before the company start making profit, and payable period tell us how long it take to recover the initial investment. Then we have conclusion, and if we conclude all my presentation, so today we study the major concept of engineering economics, including the time value of money, interest rate, present worth, annual worth, capital recovery, interest rate of return, and many more. So we also learned that the engineering economics is not only about the mathematics, it's about making smart, logical, and financial sound engineering decision. These tools help engineer to reduce cost, increase profits, and manage risk, and select the best alternative for every project. In today competitive world, technical knowledge alone is not enough. A successful engineer must also understand economic decision making. So I hope my presentation helped you understand how engineering economics is applied in real engineering projects. So thank you so much for your time and attention. Khuda Hafiz. Thank you so much.